Schmidt theorem. This guy says, hey, if you have a bunch of vectors in inner space V, then you can basically form an orthogonal basis for V by completing the process. W1 is V1, W2 is V2 minus, well, here you have the orthogonal projection of V2 onto W1, and then you continue this process. So you're basically creating an orthogonal basis for V. And if you do the division by the norm, you can make them to be unit vector as well. Let's go over one example together. This example says, suppose you have B as a basis for the plane 1 and 1, 0 and 1 is a basis for the plane. Find an orthonormal basis for the plane. We're going to apply Schmidt steps. So W1 and V1 are the same thing. Suppose this is V1 and this is V2. Vector 1 and 1. Then W2 is going to be V2, which is 0 and 1, minus the dot product between V2 and W1. So V2, let's just copy down V2, 0 and 1 here. So you get 0 plus 1 divided by W1, 1 plus 1, and times W1, which is your vector V1, and this guy is equal to 0 and 1, minus a half times 1 and 1. So you get 0 minus a half, negative a half, and 1 minus a half, which is a half. So this is your W2. Based on Schmidt method, we expect this new basis, W1 and W2, which is basically 1 and 1, negative a half and a half. These two are orthogonal and they form a basis. Check to see if W1 is perpendicular to W2. You get negative a half plus a half, which is 0. So they are orthogonal. But if I ask you to normalize these, you're basically saying that, hey, I have W1 over magnitude of W1 and W2 divided by magnitude of W2. So basically you have 1 and 1 divided by square root of 2 and negative a half, and a half divided by square root of 1/4 plus 1/4, or a half. You can simplify this as well. You get these two vectors that are both normal and they are forming a basis for them. So basically you have 1 over square root of 2, 1 over square root of 2, and then you can just flip this. You get negative square root of 2 over 2 and square root of 2 over 2.